Hi there. So in this video I'm going to describe how to generate random numbers which are distributed as a Gaussian function. So just a quick overview. So when it comes to generating random numbers, you'll generally use one of the inbuilt functions in your programming language. So I'm just going to use C++ as an example here, and generally the function which is used is rand, and you can seed this to make it less quasi-random, but basically it's a deterministic random number. So if you want a number between 1 and 0, you'll use some code like the following, where there's a set constant, which is the maximum number that the rand function generates, and you just divide rand by this constant to get a value between 0 and 1. And if you want to, for example, get a random number between two values, say 10 and 20, you'll use some code such as the following, where you just take the random number between 0 and 1 and then translate it to being between 10 and 20. And if you were to run this code, for example, 100 times, you'll get a distribution like we have here. So this is just on the y-axis, we have the number of times a random number occurs, and on the x-axis is the number. Basically, it's a histogram, so the values are binned into integer values, so between 10 and 11 will go into the first bar, for example. And as you increase the number of random numbers, slowly up from 100 to 10,000 to 1,000,000, you'll see that your distribution becomes much more uniform. And in the limit of n equals infinity, you will get exactly a flat distribution. So that's fine. Okay, so that's fine, but for many applications, you don't necessarily want to have uniformly distributed random numbers. For example, you may have a situation where you want values of a certain number, such as 5 in this example, to be a lot more likely than those at 0 and 10, for example. And in many cases of probability theory and a variety of applications, a Gaussian distribution is often used to encapsulate that. So it's this sort of ubiquitous bell curve shaped function. And the analytical form of this function is as the following. So basically there are three parameters. There's a, mu, and sigma. So in this example, we have set a equal to 1, and that's just basically the amplitude of the function. Mu, which is the mean, we have set equal to 5. And sigma, which is the standard deviation, we have set equal to 2. And basically you put in a parameter x, and you'll get the probability of that number occurring on the y-axis. Okay, to generate a number which is distributed as a Gaussian, you have to use what's called the Box-Muller Transform. This is probably the most used technique to get a randomly Gaussianly distributed number. So how does it work? So basically what you need is you actually need to create two uniformly distributed variables, and we label those u1 and u2, and they are set in the range 0 to 1. Then we use this transform here, and there are actually two transforms which give us numbers which are distributed as a normal. That's basically a particular type of Gaussian which has a mean of 0 and a standard deviation of 1. And you notice there are two possibilities here. Both of these are Gaussianly distributed random numbers, and you may only, for example, need to use one. But if you're producing a lot of numbers, it's maybe advantageous computationally to use both of these functions to save processing time, because random number generation can be reasonably computationally intensive. Okay, so the normal distribution is basically just a Gaussian, a particular type of Gaussian, where the mean indicated by mu is equal to 0, the standard deviation is equal to 1, and the amplitude is equal to this constant 1 over 2 pi. And that's just a normalization constant, which means that if you integrate the normal distribution from -infinity to infinity, you get 1. Okay, so that's what the Box-Muller transform gives us. So if you were to run the calculation 100 times, you'll get something like the following. So the red line again is just a histogram showing the number of occurrences of each of the random numbers set into particular bins, and the blue line is the analytical normal distribution. I've normalized the height here because on the y-axis we have count, so this is obviously a function of the number of number of times you run the random number generator. And then as you go up in n, you find that the distribution more and more closely matches the normal function, normal distribution. So that's basically it. The only thing you have to do is, if you're not necessarily interested in a normal function, if you're interested in a Gaussian function, you need to do a translation to get your normal into a Gaussian. It's very straightforward and it's not computationally intensive. So basically, yeah, what we want to do, we want to go from the normal function to something where the mean is not necessarily 0 and the standard deviation is not necessarily equal to 1. So the way we do that, we just run a translation on our Box-Muller variable. So the first thing you do is you multiply the random number by the standard deviation, and then you just add the mean. So it's very straightforward indeed. And this is the result. So as you go from on the left-hand side, we have the normal distribution, and on the right-hand side, we have a Gaussian, and this is with the values we mentioned before, standard deviation of 2 and the mean of 5. So it's a very straightforward calculation to do. There is one last thing that's reasonably important, and that's to do, there's one way that this can fail if you're not particularly careful, and it's a little subtlety, and it's an intermittent problem, so it can be quite hard to identify if you're not aware of it, if you're not looking for it. But basically what we're doing, we're producing random numbers between 0 and 1, and if you're using something like a double, the precision of a double is finite. So if you create enough of these values, if you create enough random numbers, eventually you will reach 0 and you also will reach 1 as the outcome, not approximately exactly these numbers. And you notice in our transform, we're taking the natural log of u in these equations. So log natural 0 is undefined. If it's 1, it's okay, that's fine. But if it's 0, that's a problem, because basically the code will fail and it will crash, and it may not be clear why that is immediately. So the one way to get around that is just to have some decision statement. Just if u1 is equal to 0, just set your variable, your output variable equal to 0. Because it's so infrequent, it won't affect your distribution significantly unless you're really, really concerned with accuracy. But if it's a Monte Carlo simulation or something, it shouldn't matter at all. So that's just the one last thing to be aware of when you're doing this, but otherwise it's a very straightforward. Okay, thank you very much for watching. If you like my videos, please subscribe, and yes, thanks again.